Now we're going to find the points on the cone z squared equals x squared plus y squared that are closest to the point 420. The equation of the cone is our constraint, and we can see that it becomes x squared plus y squared minus z squared is equal to 0. Therefore, x squared plus y squared minus z squared is g. F is going to be related to the distance. And we know that the distance between 2 points in space is the distance between 2 points in space is given by x minus x1, so x minus 4, the quantity squared, plus y minus y1, so y minus 2, the quantity squared, plus z minus 0, or z minus z1, right, which is 0, the quantity squared. Minimizing a distance is the same thing as minimizing the square of the distance, so we square both sides of this, and we get uppercase D this time is equal to x minus 4, the quantity squared, plus y minus 2, the quantity squared, plus z squared. And I'm only using an uppercase D to distinguish it from the lowercase d that we used when we wrote down the distance. Folks, this is our function f of x, y, z. From the equations we see here, we can see that del f is equal to the vector 2 times the quantity of x minus 4 using the power rule, 2 times the quantity of y minus 2, 2z. We can also see that del g is equal to 2x, 2y, negative 2z. Our equation del f equals lambda del g then gives us the system that we need. The first equation is 2x minus 8 is equal to 2 lambda x. The second is 2y minus 4 is equal to 2 lambda y. And 2z is equal to negative 2 lambda z. Those are equations 1, 2, and 3 from the gradient vectors. But then we have our constraint equation, which is our fourth equation, x squared plus y squared. I'll give it as equals negative or equals z squared. That works for me. Now, as I kind of alluded to before, there's not one way to proceed once we have these equations here. We just kind of look and see things that are possible. Like, for instance, could x be 0? Could lambda be 0? What's going on with the equations we're looking at? I'd like to zero in on the third equation. It says that 2z is equal to negative 2 lambda z. Well, if we divide out the 2's and the z's, then we get that lambda is equal to negative 1. If lambda is equal to negative 1, then the first equation gives us that 2x minus 8 is equal to negative 2x, which would mean that x is equal to 2. The second equation would give us that 2y minus 4 is equal to negative 2y, which means that y is equal to 1. Our constraint equation will then give us z. If x is 2 and y is 1, then we have that z squared is equal to 5, or z is equal to plus or minus the square root of 5. So this time we did this in the order of finding lambda, and then finding x, finding y, and using the constraint equation to then find z. Now, if we go back to the original statement of the problem here, find points on the cone that are closest to 420, we're finding points, not the actual distance. Therefore, the points that are closest are 2, 1, plus or minus the square root of 5. And I would encourage you to look at GeoGebra and see that this makes sense.